In thermodynamics, entropy is the measure of disorder. In distributed databases, it represents the exact degree of state divergence between nodes. When a network partition occurs, data writes will fail to reach every server. To maintain high availability, the database accepts the write on the healthy nodes and allows the isolated replicas to temporarily fall out of sync. This means eventual consistency is not a passive waiting game. The database must continuously run mathematical reconciliation protocols called anti-entropy mechanisms to force the diverging nodes back into alignment. We split these protocols into two categories: foreground processes that piggyback directly on client read and write requests, and background processes that run deep in the system to silently hunt for missing records. Scaling a database requires accepting entropy as a mathematical baseline. Building a robust system means shifting the focus to the efficiency of data repair and the speed of metadata dissemination. The most direct foreground mechanism is read repair. It detects and fixes divergences dynamically at the exact moment a client asks for the data. When a query hits the database, a coordinator node optimistically requests the same data from multiple replicas, expecting identical responses. The coordinator cross-references the returned data. If one server sends an older version, the coordinator spots the mismatch, delivers the correct result to the user, and immediately sends the updated data back to the lagging node. This can run as a blocking or asynchronous operation. Blocking read repairs force the client request to wait until the lagging replica acknowledges the update. This guarantees that any future reads will return the correct updated value, a property called read monotonicity, though it adds slight latency. Read repair is efficient because it targets active data, but it leaves cold, unqueried data vulnerable to permanent divergence. On the right side, the distributed system needs a robust fail-safe for when a primary node drops completely offline. Systems like REAC use a sloppy quorum. If the designated replica is down, the database drafts a healthy non-replica node to stand in and accept the write temporarily. The stand-in proxy node holds the write, but it attaches a piece of metadata, a hint, indicating the exact server where the data actually belongs. As soon as the original target recovers, the proxy forwards the hinted data. Once the target confirms receipt, the proxy deletes its local copy, restoring the exact replica count. Sloppy quorums paired with hinted handoff prioritize write availability, but they don't resolve nodes that drift out of sync over long periods of isolation. This brings us to background anti-entropy. Transferring millions of rows of data across a network just to find a few missing records would consume immense bandwidth. This diagram illustrates a Merkle tree, the solution to the bulk data comparison problem. The database scans its storage tables, hashing sequential chunks of raw data. It then hashes those hashes together, building upward until it forms a single, compact hierarchical representation of the entire dataset. During reconciliation, replicas exchange only the top hash. If they match, the dataset is in sync. If top hashes diverge, the system moves down one tier, comparing subhashes. It traces the divergent path downward, ignoring matching branches to quickly isolate the exact missing records. Merkle trees trade computational precision for a massive reduction in search scope, ensuring replicas only transmit the specific blocks that require repair. Merkle trees isolate what data is missing, but they ignore the causal sequence, the historical order in which those writes occurred. This matrix shows a bitmap version vector, a mechanism that tracks the timeline of replica states using node-local logical clocks. Every coordinated write in the system is represented by a dot, an event tracked by a node-local sequence number. Every square on this grid represents one of those causal events. A contiguous block of filled squares proves that a node has seen every consecutive light up to that specific sequence number. The white gaps represent missing causal events. When updates arrive out of order or a network link drops, the sequence breaks, flagging a verifiable conflict in the node's history. To resolve this, nodes use a dotted causal container. This structure maps those missing dots to their actual data records, allowing nodes to exchange the precise pieces needed to patch the timeline. Bitmap version vectors reconstruct exact causal histories without needing to rescan full tables, optimizing for both completeness and recency. Beyond synchronizing data, distributed systems must continuously propagate vital cluster-wide metadata, like schema changes or sudden node failures. Relying on a single coordinator to broadcast these updates fails in large systems due to single-point bottlenecks and unreliable connections. Psychologist Carl Jung observed that masses are breeding grounds for psychic epidemics. Database engineers applied this human sociology to network architecture, creating gossip protocols modeled on viral infections. An infective node holding an update randomly selects a set number of peers, the fanout, and spreads it. Those peers repeat the cycle until the entire cluster is infected, and eventually loses interest in spreading the message. Pure gossip is practically indestructible against network failures, but its randomized nature creates a massive penalty in duplicated message traffic. Modern systems tame pure gossip using hybrid overlay networks, such as plum trees. Under normal conditions, nodes use a fixed spanning tree, the eager push network, to send full metadata payloads with zero redundancy and minimal latency. Simultaneously, the system maintains a backup, the lazy push network. Across these random connections, nodes only forward lightweight message IDs, not the full data. If a node receives an ID via the lazy network that it hasn't seen on the main tree, it proves an active link is broken. The node queries the gossip peer for the full payload, pulling the data across the gap and repairing the spanning tree structure. Plum trees brilliantly combine the efficiency of a rigid broadcast tree with the high availability of a viral epidemic. These topologies must handle constant churn, the high rate of nodes joining and failing. Requiring every node to maintain an up-to-date global list of every other peer creates a significant bottleneck. The HyperView protocol functions as a peer sampling service, limiting how much of the network any single node needs to track. Each node maintains two distinct lists, a small active view of direct neighbors and a larger passive view of random cluster nodes used as a backup reservoir. When an active peer drops, the node instantly pulls a replacement from its passive list to establish a new connection and prevent the broadcast tree from collapsing. Partial views allow a cluster to expand without increasing the metadata overhead on individual nodes, as resilience is managed by local overlapping neighborhoods. System consistency is a continuous, calculated war against entropy, requiring highly specialized mathematical tools. To reconcile data, we prioritize availability with hinted handoffs, optimize scope with read repair, isolate bulk gaps with Merkle trees, and reconstruct causality with version vectors. To disseminate state, we maximize speed via eager plum trees, while safeguarding the cluster with lazy gossip and HyperView partial views. These invisible protocols power production systems like Cassandra and REAC. They provide the mathematical guarantees that prevent distributed infrastructure from collapsing into asynchronous chaos. Out of asynchronous chaos, these algorithms ensure that systemic convergence is mathematically inevitable.